Let's play a game. You are an incident responder. You have been notified by Okta that some suspicious activity is occurring in your environment. You don't know what, how, or when. In the same time, you see spikes rising in GitLab dashboards. You are a great incident responder, so you imagine something like this. A threat actor compromised Okta account, used SSO to access GitLab, iterate over GitLab repositories to extract a token, and return with that token back again to Okta with elevated privileges. Now, it's game over. But how can you start investigating it before it's too late? How could you detect it sooner? How would you notice if someone used SSO without authenticating beforehand? And how can you investigate GitLab logs if you don't know how they look? That's what we're here to talk about today. We want to tell you a story of threat hunting in Okta and GitLab environments. My name is Ariel Kalman, and I'm a security researcher at Mitiga. This is my friend Gabi, and he's also a security researcher at Mitiga. Here's what we are going to talk about today. We'll start with an overview of Okta, its core concepts, and the log structure it generates. Next, we'll dive into an interesting attack path in Okta and how to detect it effectively. Moving on to GitLab, we'll discuss different logs and various concepts related to its security. We'll explore attack scenarios on GitLab and how to hunt for potential security threats. Finally, we'll wrap up everything with security remediations for both platforms. Before we begin, let's clarify a fundamental concept. An identity provider, or IDP, authenticates users and manages their access to applications and services by verifying credentials. Okta is a type of IDP, and it allows users to access multiple applications using a single password, one MFA device, and unified security controls via SSO. While it streamlines access and enhances security, does it also create a single point of failure? Could compromising one user grant access to multiple applications, not just one? Perhaps this is why, despite Okta being one of the most widely used identity providers globally, it is also a prime target for attackers. Over the past 2 years, Okta had experienced multiple significant breaches. The most recent one occurred just 4 weeks ago. Many customers mistakenly treat Okta as a comprehensive security solution. However, breaches like these highlight the need for a more proactive approach. Instead of solely relying on Okta's security controls, you have to collect and analyze Okta logs and actively engage in threat hunting. But what do Okta logs even look like? Let's make it simple. In the next few slides, we'll dive into Okta logs. We'll categorize the hundreds of event types into 4 main groups to simplify it. We'll display the system log schema and highlight significant fields that hunters must know and use. Finally, we'll show you what is not logged in Okta, focusing on how the threat actors can enumerate your environment without being detected. Okta has nearly 1,000 different event types. Sometimes it's hard to differentiate between 2 event types. For example, take a look at these 2. The first is application.policy.signon.update. The second is app.policy.signon.update. The description for both, update app sign-on policy. A bit confusing, isn't it? So apparently, Okta differentiates between app and application, but they do not consistently stick to this distinction. So to make it simple, we divided all Okta event types into 4 groups. First is authentication events, where you can see user logins and logouts, multi-factor authentication events, single sign-on application access, and more. The second group is management events, where you can mainly see admin activity, including policy modifications, group alterations, and role assignments. The third group is application events, where you can see the actual integration between Okta and different apps. In this group, you can see OAuth token generation and usage, and also integration changes between Okta and different apps. The fourth group is security events, which are somewhat mysterious. These are security alerts generated by Okta's security products, such as Threat Insight. Because we don't know the logic behind them, it's hard to trust them. They are often spammy and not very informative, but if you correlate them with anomalous user behavior, they might be insightful. Now, let's move on to the one and only Okta event log. This is the sole event log for Okta, where each operation is recorded. It contains a variety of properties every log has, like IP address, user agent, date, and time. But it also contains more interesting ones. For example, the actor property, which is the entity that performs an action. Okta defines 4 types of entities: user, application, IP address, and system principal, which represent an internal service of Okta. The second property is the target property, which is the entity that the action was performed on. Okta defines dozens of different resource types, including certificate, MFA device, user, or group. The third property is the debug context property, which contains one field called debug data that may have a variety of forensic information that can help you understand why an event is suspected to be suspicious. When investigating an incident, it's crucial to know that you can't see everything. Let's discuss what is not logged in Okta, focusing on how threat actors can enumerate your environment. First, all GET requests to Okta's API are not logged. Using Okta's API, a threat actor can enumerate your environment, listing applications, groups, policies, and more. For example, here you can see application enumeration by a threat actor, me, without being logged anywhere. Second, some post requests to Okta's API are not logged. Generally, post requests that don't create an event type are not logged, in contrast to user creation or policy modification. Third, all read access to Okta's admin console is not logged. It means that if a threat actor connected to your admin console, you can't see his read-only activity. Now, let's move on to the most exciting part of Okta. Over the next few slides, we'll dive into a complete attack path in Okta and how to detect each step. For each step of the attack, we'll present 2 detections and key forensic indicators that you can use in your environment. The attack starts in Okta with user compromise and MFA bypass. It then abuses SSO to access GitLab. We'll skip GitLab part for now, since Gabi will cover that later. Finally, we'll return back to Okta with elevated privileges and create persistence in a unique way. Let's dive into each step. The first step is initial access. The threat actor needs to have a foothold in your environment, often achieved by obtaining users' password through methods like password spray or phishing attack. The next step is to bypass MFA. We'll present 2 detections for it. First is MFA fatigue. This occurs when a threat actor repeatedly tries to log in to a real user's account, triggering push notifications. After multiple denials, the user may approve it to stop the notifications. Detect this by looking for multiple MFA failures followed by a successful one. The second detection is impossible traveler. This occurs when you detect 2 events from geographically distant places in a short time period. For example, if you see a login attempt from Tel Aviv followed by an MFA approval from Tehran, it may raise suspicion. Detect this by creating a geovelocity function that will assess if the distance and time differences between events make sense. The second step of the attack involves SSO. Once the threat actor obtains access to an account, he can see the accessible applications by this user and can pivot using SSO. Detect this by creating a detection called New Country SSO, which detects an SSO connection made from a country you haven't seen before for this particular user. To reduce false positive, filter out new users and common workplaces. The second detection is malicious SSO. While we haven't delved into Okta Threat Insight extensively, it's a security product by Okta that analyzes and creates alerts for potentially malicious IP addresses. Although it may create some false positives, combining its alerts with suspicious SSO connections reduces false positives significantly. The final phase of the attack, after which I will pass the torch to Gabi to continue the talk on GitLab, involves a persistence mechanism that Okta themselves have observed in the wild just 4 weeks ago. Assuming the threat actor obtained an admin token and now has elevated privileges, how can they persist their privileges? They can abuse Okta's core settings. CORS stands for Cross-Origin Resource Sharing, is a security feature in web browsers that controls which web applications can interact with resources from different domains on the internet. For example, if the site apple.com tries to fetch cookies from the site google.com, CORS determine whether the request is allowed, ensuring that only trusted domains can interact with your site. A threat actor can abuse Okta's core settings to allow his malicious domain interact with Okta's API and bypass your detections. For example, here, you can see me adding a malicious domain to Okta's core settings and allow him to interact with Okta's API. Now, let's move on to talk on GitLab with Gabi.
Thank you, Ariel. So, officially, our attacker has moved from Okta to our GitLab environment. But before we get into the details and concepts, there's a bit more to GitLab than you might think. GitLab has more than 31 million users. Yes, 31 million users. Who knew? Additionally, they're used by over 100,000 companies worldwide, and most of their use cases are for company code. Meaning, it's not only well dispersed, it's also a prime goal for an attacker to access this. With that being said, let's understand what is GitLab. GitLab is generally a one-stop shop for all your development lifecycle needs, starting from code repository and version control to CI/CD pipelines, to managing tickets called issues, kind of similar to Jira, an internal wiki, and much more. But for the sake of our talk, we'll focus on this, that it's a repository. So GitLab has a few different offerings. It has 3 offerings, one being a self-managed, one being a SaaS implementation, and one being a dedicated one. The self-managed is managed by our own infrastructure, which gives us full control and high place for customization. The SaaS implementation is completely managed by GitLab.com, which means we don't have that much room for customization, but on the other hand, we have a very low overhead for managing. And the dedicated GitLab is managed by GitLab, but it's considered a single tenant, which means it's managed for a specific case, which gives us some room for customization, but it's usually used for compliance and data residency. In our talk, we'll focus on the SaaS implementation and the logs we could achieve through the REST API. It's also key to note that the self-managed API, self-managed GitLab has additional logs that we will not get through the SaaS implementation. So let's move on to some concepts we have in GitLab. Although GitLab has a plethora of features and concepts, we'll focus on 2 for our threat hunting actions, one being groups and one being projects. A group is essentially an organizational unit that could be represented by a company or a division. So, for example, we could have a group being company X, having a subgroup called division A. Under that, we will have something that could be a project. A project could represent our code repository or some product or feature. And what we could have here is, again, company X has subgroup A, which has project 1, which is one product, and project 2, which is the other product. So with that being said, we understood that GitLab is well dispersed, its prime attacker, and some of its key offerings. Let's move on to some of the logs we could find in the SaaS REST API implementation and move on to our threat hunting process. GitLab offers us 2 main logs that we could collect via REST API. We have the events logs and we have the audit logs. The events logs are known as contribution events. These are stuff like Git operations, when we're pushing code, committing, creating a new branch, etc. Some important fields we could see from the logs. Yes, I'm aware this looks horrible, but this is just to get it into your mind before we dive in, or stuff like a time it was created, an author, which is the initiator of an operation, an event name, and a target is what we did the operation on. So let's dive into one of these cases. Here, we could see that this dude did improve on this merge request, which is our target title. And we could see that the target type was a merge request. Fairly simple, but this is what kind of closes the small story of what we could see in events logs, but these are only some key fields. Next, we have something called the audit logs. These are for group configuration and management of administration operations, like creating new users, new groups, new repository, and creating project access tokens. Some important fields we could see here can be similar to what we saw in the events logs, but we also have an addition of an IP address here, and here the event, so-called, is called custom message. So let's dive deep into one of these cases. In this case, we could see that that dude created a project access token called BSidesTLV as the target title, and we could see as the entity path on which project they created this token. This kind of gives us a look of what we could look for. And for you researchers or curious people out there, try to understand why when we create a project access token, it's considered a personal access token. But I didn't mention what are project access tokens. You're like, what are you talking about? So for that, let's mention that access tokens in GitLabs are essentially a string that allows us to connect with HTTP and Git operations to our GitLab implementation without needing to authenticate. We just need to show this token and we're able to operate. So with that question in mind, let's go on a hunt. But before we start our hunt, there's two things we want to mention. One, a hunt is a assumed breach kind of like method. We're assuming someone's inside and we're actively looking for possible malicious activities. And what we're going to show here today is something to spark your imagination. We're looking for stuff that you might take from here, but you would know your GitLab environment the best, and therefore we trust you to know your own hunts. But where did it all start? We mentioned that our attacker abused their case in Okta and managed to pivot all the way back to GitLab. And in this case, we could see that the attacker dude had a SAML group connection with our audit logs, which indicates that they came here through an SSO. So, our attacker is right now in GitLab environment. And Ariel mentioned previously that they want to have a key that they could connect back to Okta. So, something they might decide they want to do is to download a full project. GitLab allows us to have an archive download of full projects. So stuff we could look for are event names that could say repository download started. But enrichments could give us extra enhancements to ask ourselves the right questions when we're hunting, right? Is this user supposed to download these things? When did this happen? What IP did this come from? And how many downloads are we expecting to see in our organization? So our attacker has their access token, they're very happy, but they want to keep a foothold in our GitLab environment. So they have two things they might be doing. The first is creating a permissive access token. As mentioned before, an access token will allow us access back to our GitLab environment through REST APIs without needing to authenticate. So stuff we could look for here is, again, as mentioned before, a personal access token, but our custom message will tell us that we created a project access token, which gives us a scope of an access token to the whole project, and we might look for permissive API permissions or scopes, like writing APIs, creating runners for CI/CD, etc. Things we could enrich here are expiration dates. For example, this won't be in the logs, but if you have access to your system and you see an expiration date which doesn't usually stand with the standards of your company, it might indicate malicious use. How many tokens or project access tokens do we usually expect to have in our environment? This is something you could also consider. Again, IP, location, user agents are questions you could ask yourselves. But with that being said, let's have a small chat about bot users. GitLab's documentation states that whenever we create a project access token, we're creating a representation of something called a bot user, which is usually for internal processes and automation, that will represent any action done by this bot user, by this token. Meaning that we will see something like project or group _ID _bot something. Now, why an attacker might want to use this is that every time we create a project access token, not only does it give us access to our GitLab environment, it doesn't cost us a seat. A seat in GitLab is basically an allowance of how many users we're allowed to have in our SaaS implementation. So if we don't want to alert any cases for additional seats, a bot user will not alert it because it's not considered a seat. So we could look for unusual spikes in bot operations and unusual resources. We know our environment, we know where they're supposed to occur, and if it's an automation account, what time is this happening? Why is my bot user accessing a bunch of things? So with that being said, the second method they might want to do for persistence is what I'd consider the old but gold, adding another user that they might have access to, giving them additional permissions. We will look for something that we're adding to a user access, kind of permissions such as owner or maintainer, which are highly privileged, but something you might want to filter out is a membership created event, because maybe we are supposed to have a new owner or maintainer of our code. Additional things we might want to see here are like organizational context. How many administrators or owners, maintainers are we supposed to have? Was this user supposed to be added, supposed to give these permissions? Where did this come from? And user agent is always a nice thing to have. So we have the data we've downloaded. We also have a way to get back into our GitLab environment. But unfortunately, something happened this morning. The attacker woke up, and they couldn't find any matching socks. So that drove them crazy, and they wanted to go full kamikaze and decided to make our project and our group completely public for the whole world to access because they need to have their socks ready. So what we could look for here is a custom message with the visibility or visibility level turning from private to public. Additional information we could look for here is how many of these projects or repositories are supposed to be public. We could also look for when this happened, where did it come from, and how many people are supposed to access this that frequently, and most important, do we have matching socks for our attacker? So some security remediations we have. In Okta, first, review your MFA that everyone has MFA. I mean, do I really need to stress this out? Additionally, you have to check that your admin console, as Ariel mentioned before, that sometimes things aren't logged there, we want it to be secure, so we need to enforce MFA. Additionally, we can enforce network policies, which will limit the access to our Okta environment. But there is something of an early access feature that will allow us to also have network policies with SSWS tokens, because previously, you could have still logged in with a token even if you were on a limited network policy. And finally, review and possibly revoke your API tokens. Do you have any Okta API tokens around that might lead people to start this whole process at the beginning? Now let's talk about the GitLab recommendations we have. GitLab allows us to have a feature that's called secret detection. Enable it. It searches your repository actively for codes, for keys, passwords, etc. We could also enforce MFA on our GitLab implementation rather than just a user or password. It's a feature, somehow you need to turn it on. And we could restrict IP access based on network CIDR ranges and by email domains to our environment. And finally, we also have a small tick that could prevent users from creating a project or a group access token to our environment. It's a small tick, but it could cause us to be more protected from attackers losing their socks. So, what next? Tomorrow, see if you're available to have all your logs right for you, right? Are you ready for investigating a possible case? Do you have all your logs ingested? In a week from now, study your logs, check your patterns. How does your Okta environment look like? What are you expecting to see in your GitLab stages? And in a month from now, actively conduct a hunt in your environments. Did your Okta users move from one system to another? Is there anything weird going on in your GitLab environment? But if there's one thing I could have you all take away from here today is, even though we can't always control or trust our security systems, we can always hunt our security systems. Thank you very much. We were Ariel and Gavriel, and this is our link to Okta.